Hello everyone, and welcome to another day of pre-calculus review. When we touched off on the last session, we started our concept on conic sections, and we talked about what circles are. To go over them, let's look at this. So, what are conic sections again? Conic sections are, well, quite literally, bits and pieces of a larger cone. You take a slice here, it becomes a hyperbola. You take a slice here, becomes a parabola. Take a slice here, becomes a circle. You take a slice here, it becomes an ellipse. That was the general concept. Now, before we move on to ellipses, let's finish going over circles too. So, what are the qualities of a circle? Well, to draw a circle, what you need to know is essentially the radius of the circle, which is the distance from the central point, and the position of it. And that's all you need because the distance will be the same around every point, and you know where to draw it on the graph. So today we're going to cover what ellipses are. So an ellipse is the shape of an ellipse is just a bent circle in a sense. Like a circle that's been pressed down, pressed to the side this way, it can be long, it can be diagonally this way. And what they are is when you have a cone, they're the non-horizontal slash of a conic section. I mean, like if you were to take a horizontal cut of this, you would get a perfect circle, right? But if that circle is not exact, you get a diagonal ellipse. Now, these things are different, aren't they? Well, what would you need to draw an ellipse? Well, it's a lot more complicated than a circle because a circle was easy to draw under the rule that it had the same distance throughout the entire thing, right? However, for an ellipse, you need to know the distance from the central point to the edges changes all throughout. And the variety in this difference of lengths can change. For example, you could have a slight ellipse, and you could also have a long ellipse like this. These changes depend on whether the cut of the ellipse is diagonally steep or more uh, less steep, as in this would make something closer to this. This would be this. Well, this would be something closer to this. That is the shape. Now, the thing about these ellipses are that to help us solve this, to help us write out an ellipse, in math, we generally need 6 different points of an ellipse. What these points are is, well, these ones are a bit more obvious. You need to see where it ends on horizontally and vertically. So that's 1, 2, 3, 4. And you need 2 additional points called the foci. Now, these foci exist on the longer side of the ellipse, which means that, see how this is like a stretch out this way? The foci are horizontal. If this ellipse were to be vertically long, the foci would be vertical here. Now, what the foci helps us determine is something called the eccentricity of the ellipse. What this means is that depending on how far out the foci are, it changes. It's a representation of how essentially flattened out or how close to a circle an ellipse is. Sorry, had to fix something real quick. All right, is the mic working fine now? All right, so let's take a look at what a graph looks like. So if we were to graph an ellipse, let's move this out of the way. First, let's start with the equation of what we thought to be a circle, right? It was x squared plus y squared plus the square of the radius, right? Well, for an ellipse, instead of having the x squared plus y equal to the radius squared, in an ellipse, it is always equal to 1. And the equation looks something like x squared over a squared plus y squared over b squared. Now, what this uh, what these A and B mean are essentially the points of a circle. So A is the distance from one of the sides, from the center of the point, while B is from another side. Because in this case, we are showing the smallest point, like the shortest distance, and the longest distance. This also means that the more eccentric ellipses, the disparity between the A value and the B value is. Now, how you exactly get these values are, if you think about it, to get it to x squared plus y squared, these things would have been multiplied over from the other side, right? Well, you see how it was essentially r squared here? We're essentially dividing that into two forms and then splitting it up to associate to them to x or y. And generally, the a value tends to be the longer side. Now, I mean, it could be x squared over b squared plus y squared a. But what's important is that generally you put the a value as the larger value. It's not actually essential for an ellipse because no matter what order you put it, as long as the x and y numbers are correct, then you plug them in. They're technically correct because it's addition. 1 plus 2 equals 2 plus 1. But because this rule is also applied when talking to hyperbolas, in which their equation looks something like x squared over a squared minus y squared over b squared, it's important to keep it consistent and give it a certain pattern so that it's easier for you to memorize it. Now, let's look at how the foci of an ellipse is calculated. So let's draw an ellipse again, right? Assuming we have the midpoint here, let's draw a simple coordinate plane here. Let's say this point is A and this point is B. Now, we're gonna label the foci as C because A and B are given. how would we calculate this value of c? Well, the general idea is that you would calculate this value by doing so. One thing you need to know is that the foci is located at a distance of a diagonal line originating from B. So if you draw a diagonal from the B point to a foci, that distance will be equal to A. So you know that, and this sort of makes a triangle, right? This is a B, this is a A, and this value is a C. So you can apply the Pythagorean theorem here. In order to calculate the C, C is equal to A squared equals B squared plus C squared, or C squared equals A squared minus B squared. And remember, this is why it's important to remember which one you put as A and which one you put as B, because, well, if you mess up this calculation, it's just going to give you the wrong foci value. It's actually just going to give you a negative number, which is not possible to exist on a coordinate plane. Because you can't have a negative distance, at least not on a coordinate plane. You only really need to think about you can generally eliminate negative values outside of when you get to polar values later on in precalculus. And oh, and let's go over this too. This should be the same rule as before, but do you guys know how we determine the midpoint? Well, you can just think back to the circle for this, because remember how it was x squared, or like x minus h squared and plus y minus k squared for the variance in the x and the y, and like where the midpoint of it was? Well, it's the same thing for here, except that you're just putting it on top of a squared and b squared. And 1. And remember, it's negative, so whatever you put in, it will go in the opposite direction. If you put in 5, that means that it's going to say x minus 5, but it's actually just going to be 5 to the right instead of 5 to the left. Now, let's try graphing an ellipse. So let's say you get an equation, just going to make this one up really quick. X minus 2 squared plus y plus 1 squared over 9, 4 equals 1. So to start us off, let's start by figuring out what A and B are. So A and B are, well, you take the square root of the denominator of the larger value. The larger value is always A, so it is 3. A equals 3. And B, the square root of 4 equals 2, so B equals 2. Applying this that equation rule from earlier, applying this Pythagorean theorem, we have c squared equals a squared plus b squared, which is 9 plus 4, so square root of 13. Now let's figure out where the midpoint of it will be on, and it is minus 2 to the left. I mean, 2 x equals 2 and y equals -1. To draw this, draw a coordinate plane. 1, 2, -1. Draw from here. 1, 2, 3. A value is reaching -1, and 3, 4, 5. 5 here. And it extends up 2, so 1, 2. And reaching -3 here. It's going to look like this, and then you draw the foci at square root of 13, which, if you use a calculator, square root of 13 equals something around 3.6-ish. So we'll draw the point 1, 2, 3. Wait. Oh. Give me a second. I think I might have messed up somewhere. 9, 4. Oh yeah, my bad. I messed up this equation here. In this case, because a squared, differently from the normal Pythagorean theorem, a squared is equal to b squared plus c squared. So this means that 9 minus 4 equals 5. So square root of 5 is equal to the distance from the midpoint to the foci. So square root of 5 is 2.23, which means 1, 2 around here, 1, 2 around here. Then you just try your best to draw like an ellipse that relatively fits here. Now, what most ellipse problems will result in something like this. It's gonna give you certain information, not always the whole equation, but it's gonna give you certain aspects of a problem, and it's gonna be up to you to figure out the other information and finish graphing it. So, for example, instead of having to derive all that information, it could just give you straight out. Let's say the midpoint exists at 0, 0, the origin. Uh, say the value of A is equal to 5. The value of B is equal to 1. Now, with just that, it could ask you to figure out the equation. I mean, you can definitely do that. After all, this is all the information that you can directly get from the equation that is written out. It's 0, 0, right? A assuming that x is the long side. Oh, and it should also determine which axis the foci exist on. So A is 5, assuming this is here, and 1 minus 1, -5. And now for the foci, C, make a triangle. This value is A, as I said. This is B, and this is C, so square root of 5 is equal to 1 plus square root of C. I mean, my bad, not that. 25 equals 1 plus C squared. And the answer to this, to the square root of 24 is something around 4.9899. 4.899. Now, the important one thing to note is that you noticed how close the foci is to the A. It's only a gap of like 0.1 between where the foci is located and to the distance of A. This is because the value of this is very flat. The more flat something is, the more the closer the foci will be to the outer points. And as B and A become closer together, the foci slowly move inwards and inwards until they reach the midpoint. So if the foci essentially exist on the midpoint, then at that point it will become a circle again. And if you continue to shrink them more, it's going to expand out vertically this time. And this is essentially what makes a circle not an ellipse. The fact that the foci exist on the same coordinates as the midpoint. Let's try something similar but different this time. So in word problems, you're gonna see it something like this. The use of ellipses are commonly used to describe arched bridges. Say, so a small bridge looks something like this, right? Say this is a bridge, like a small one over like a pond or like a small river or something. Water flows through here, right? Water flows through here, and people walk on top of here. But one thing you should know about these types of bridges is that you see the gap in the middle, right? That's an ellipse, or to be exact, it's half an ellipse. But well, the rest, the other half of the ellipse exists underground. But the general design is meant to be an ellipse, but the shape of an ellipse helps support the weight. Now, in cases like this, the question would be something like, so here, things it must give you. It needs to tell you where the water is. So in this case, it's going to tell you that the water is going to exist exactly at the midpoint of the ellipse. Other times, it could exist where the ellipse stops happening. So like here, maybe. And then the rest of the actual ellipse would be here, but you would have to sort of cross out this area to figure out what the area of the ellipse would be. So it's gonna give you where the water is. After it does that, it's gonna give you the distance from either either gonna give you the thickness of this bridge and where people walk, which you just subtract here from here, or it's just gonna straight out give you this point. This point in this case will be B. It's also gonna give you how long uh the the ellipse is. Divide this in half, and that will be your A. And after that, you apply the same rules, you find for the C, and using that, you can easily figure out the general equation of the ellipse. Another common problem I saw used was in the idea of a certain building. So there are some notable buildings in the world that are famous for having some strange echoing properties. For example, someone were to scream from here and here, they would hear it at the same time no matter where they heard it from. If they shot it, if they screamed this way, they would hear it at the same time. They screamed upwards, if they would hear it later at the same strengths. But in outside, this is not the case. If you shoot scream upwards, well, they're not going to hear it out as well. If you shoot backwards, they might not hear it at all. But special about this is that from the foci, the total distance between a wall and a foci is always equal. So what this means is that, say we have this here, right? We have another ellipse here, and you have 2 points here. Let's say we had a loose string hanging from here. It's loose enough that if you were to pull on a specific point, it hits the edge. If you dragged this point around 2 points, you would be able to create an ellipse. This is actually how you draw an ellipse in real life, like without any dimension. It's like the equivalent of a compass. You take 2 points, you take a string, and draw your pencil as it tugs, and it should draw something like an ellipse. And think about it. If you have an ellipse, midpoint here, assuming the foci exist here, this distance is equal to the addition of these two distances. Now, the most important thing to take away from today's lesson is the idea of a foci. Foci generally have to do with a point in which a certain distance is fulfilled. That's gonna come up significantly in hyperbolas and not as much parabolas, but it's still an important concept to know. It's probably what defines the irregularity of conic sections compared to a normal circle. So that's going to be where we're going to wrap up the lesson for today. And thank you for watching.